Section 8 for simple harmonic motion. The periodic nature of trigonometric functions is useful for describing the motion of a point on an object that vibrates, oscillates, rotates, or is moved by a wave motion. Motion of this nature can be described by a sine or cosine function is called simple harmonic motion. The wave shape of the graphs of the functions is called a sinusoid, and the function is called a sinusoidal function. Recall that we have our two graphs, the sine graph and the cosine graph, so these are the two different ways that they can look. And remember, we've talked about how to find all these values, so just recall that that A value that's in front is our amplitude. And remember, to find the amplitude, it's always the absolute value of A is equal to the y maximum value minus the y minimum value divided by 2. That gives us the amplitude of our graph. And remember, this distance and this distance right here tells us our amplitude from our graph. Then we have our b value, which helps us determine the period of the function if we're given an equation. And so remember that your period is equal to your parent graph period divided by your b value. So you can also, if you're given a graph, find the b value by using that equation. Then we have our c value, which remember is called the phase shift. And remember, the phase shift just depends on if you're writing a sine or a cosine graph for what that is. If it's a sine graph, you can use your x maximum and x minimum values and divide that by 2 to find it. And then your d value, remember, is your vertical shift. And remember, to find your vertical shift, you can do the y maximum plus the y minimum and divide it by 2. So that's all the stuff we need to know. And one last thing that we talked about is to find the key points of your graph. Remember, the key points on your graph are the maximum, minimums, and the intercepts. And in this case, to find them, you can take the period and divide it into 4 equal parts or multiply it by 1/4. So let's just practice writing some equations since we haven't done it in a little bit. If you look at this first part, it says, write an equation of the graph shown to the right. So if we look at this graph over here, it says what type of curve displayed. Remember, when we start with a maximum and end with a maximum like this resembles a cosine graph, so it looks like a cosine graph. So however, remember that we can always make cosine into a sine graph by doing different kinds of phase shifts. So we'll talk about that as well. The period of the function, remember, is the length of time that it takes to complete one wave. So from here to here, we have a maximum to maximum for our cosine graphs. For a sine graph, notice that it would be, you would have like 3 intercept values from where it crosses the x-axis or wherever your vertical shift is. So I know that this is one wavelength, and the distance horizontally from here to here would be 20 minus 5, which is equal to 15. So I know that's the period of the function. So 15. And then it says what's the amplitude. So to find the amplitude, remember, the amplitude is the absolute value of the y maximum. So we have 6 minus -3, because my minimum is down here at -3, my maximum is here at 6, divided by 2. So I know that my amplitude is going to be equal to 9/2 or 4.5. The phase shift, if it's a cosine graph, then I can tell just by looking at this, we've shifted our graph from here all the way over to here. And really, I mean, the cosine normally starts up here, so I should say it's from here to here. So we've moved it to the right 5. So for cosine, the phase shift would be right 5. Then for the vertical shift, so which is your d value from our equation, we do the maximum plus the minimum divided by 2, which gives us 3 halves or 1.5. And as we did before, I always like to draw that line in. So I know that right here, would be my vertical shift. And the reason I like to draw my new x-axis is because it tells me if I had to make a sine equation where I would need the point to be. So then the next part says we want to write an equation for this. So cosine is going to be the easiest equation that we can write. So in order to do that, though, I need to also find my b value. So if I know my period, remember that the period is equal to 2 pi over your b value. And we said that the wavelength of the graph was 15. So if I take this equation, I can cross multiply and solve. This is over 1. So I get, over here I'm going to write it, so 15b equals 2 pi. So b equals 2 pi over 15. So that's the b value I use in my equation. So y is equal to my amplitude, which remember is this distance from here to here. And we said that we found it to be 4.5. So y equals 4.5 times the cosine of our b value, which is 2 pi over 15, times x minus our phase shift, which was 5, plus our vertical shift, 1.5. And remember, there's many different equations that we can have for this graph. So I didn't just have to do a cosine graph. I could have also turned this into a sine graph. So if I wanted to turn this into a sine graph, then I need to figure out what this x value is right there. Well, how do I do that? If I know the period is 15, then remember your key points are going by 15 divided by 4, so which would be 3.75. So if this value starts here at 5, then the next key point would be right here, which and it would be an x value of 5 plus 3.75, so 8.75. This key point would be at 12.5. All I did was take 8.75 and add another 3.5. This key point right here would be at 16.25, and the last one is at 20. So this value right here would be, again, a phase shift to the right of 8.75 for sine. So I'm going to write the sine equation underneath. So I have y equals, and if it's going down first, it would be negative 4.5 times the sine of my b value, which we said was 2 pi over 15, x minus 8.75 and plus 1.5. So that would be my sine equation. And we talked about how to do those before. So let's go ahead and look at these next two equations. For these next two equations that we have, we want to write a equation for the graph, and let's do a sine and a cosine graph. So if we look at this first one, we need to find all of those values that we talked about. So y equals a times the sine or cosine of b times x minus c plus d. So in this case, my a value, or my amplitude, is equal to my maximum, which is 4, minus my minimum, which is negative 2 divided by 2. So that would give me 6 over 2, which is equal to 3. So I know that my amplitude is 3. Then my vertical shift, which is my d value, is 4 plus negative 2 over 2. So if I do this equation here, I get negative 2 over 2, which is just, 2 over 2, which is just 1. So I know my vertical shift is here. I always like to draw that in. And then I need to figure out what one wavelength of my graph is. So it looks like it's starting off with a cosine graph here. So one wavelength would be from here all the way to here, which looks like the distance of pi. So the period is equal to pi, so I can find my b value then. So remember that the period equals 2 pi over b. So in this case, pi equals 2 pi over b. So b would be equal to 2 pi over pi, which is equal to 2. So this is, again, my b value. Then from there, the next thing I need to figure out is if I have a phase shift. For cosine, this graph would not have a phase shift because it's starting on the y-axis. So my equation for this would be y equals, and the cosine starting up, so y equals my amplitude, which is 3, times the cosine of my b value, which is 2, times my phase shift, which in this case for cosine I don't have one, and then plus my vertical shift, which is 1. So this would be the equation of my cosine graph. If I did a sine graph, there's different places I can choose. I could choose this point here, this point here, this point here, and so on. So if my period is pi, then that means my key points on my graph are going by pi times a fourth or pi over 4. So this right here is really pi over 4. And then the next one would be pi over 2, 3 pi over 4, 4 pi over 4 is just pi, so that gives me back to my one wavelength. So if I picked this point right here for my sine graph, it would be y equals -3 because it's going down first and then up, times the sine of my b value times x minus pi over 4 because we moved to the right, and then plus 1. And of course there's many equations that I can have for this graph. This is just 2 of them. Now, for this graph that we have right here, I want you guys to find a sine and a cosine equation. So find a sine and cosine equation for the graph. So again, you are completing this. And then I'll check that in class. So let's get to the heart of some of these problems and actually do an application. So for example 3, it says, as you ride the Ferris wheel, your distance from the ground varies sinusoidally with time. When the last seat is filled and the Ferris wheel starts, your seat is at the position shown in the diagram. Let t be the number of seconds that have elapsed since the Ferris wheel started. You find that it takes 12 seconds to make one revolution. The diameter of the wheel is 55 feet. When you begin, your seat is 5 feet from the ground. What is the period of the function? So remember, the period of the function would be the time it takes to go all the way around our circle, and we're starting down here at our seat level. So it said that it takes 12 seconds to make one revolution. So we've got a Ferris wheel that's moving kind of fast here, but that's okay. So we're going at a super fast speed. So that's the period of the function. Then it says the amplitude. Well, how do I find the amplitude? I need my maximum and my minimum. Well, if the diameter of the Ferris wheel is 55 feet and we're 5 feet off the ground, then I know my maximum value is going to be a value of 55 plus 5, which is of course 60. And my minimum value would be the lowest I go in my Ferris wheel, which is 5 feet above the ground. So now that I have that, I can easily find my amplitude, because your amplitude is equal to your maximum minus your minimum divided by 2. So 55 divided by 2 would be equal to 27.5 feet. So 27.5 feet. Now, we're not going to do the phase shift just yet. We'll skip over that and come back to it. So the vertical shift is also easy to find. That's your D value, remember. Your vertical shift is your maximum plus your minimum divided by 2. So 65 divided by 2, which gives me 32.5 feet. And let's go ahead and sketch a graph for this. So for my graph, I know that the period's 12 seconds. So if that's the case, then I know that my key points are going to be going by 12 over 4, which is by 3 seconds. So on here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would be 3, 6, 9, and 12. I'm going to make that 3 look a little better. I also know what my amplitude is and what my vertical shift is, so I'm going to write my vertical shift in right here. So my vertical shift, we said, was 32.5 feet. and my amplitude is 27.5 feet. So that means I'm going to go up this way and also down this way, a distance of 27.5 feet from my axis. And we actually call this as axis of oscillation because that's the axis that we're going back and forth in between. Now for this, I have to figure out where I'm starting though. It said that at time 0, my seat starts here. So if my seat's starting at 5 feet, that would be at 5 feet here. So we're starting here on my graph. That means after 3 seconds, and remember our graph is split into 4 equal parts. So if I'm starting here at 5 feet, then the next point that I'm going to hit would be after 3 seconds. And so 5 plus my amplitude, which is 27.5, gives me this next place right here, which is 32.5 feet. Then after another 3 seconds, I would be up here on my graph, which is at 60 feet because our diameter of our Ferris wheel is 55 feet and we're already 5 feet off the ground. So then I should also add in my maximum, which is 60. So for this, I know at 6 seconds I'm at 60 feet. Then I'm going to come down to here. So now I've gone down back to 32.5 feet, and then I'm back at 5 feet after 3 more seconds. So my graph starts to take shape and would look something like this if we were to map it out. So that would be the graph. Now for this, if I'm making a cosine graph, I don't have a phase shift. If I make a sine graph, I would have to shift my graph to this point right there. So let's go ahead and take a look at this. So to write an equation, we're going to do both the sine and the cosine. So for my cosine graph, we also need to find what the b value is. So to find the b value, you can just do 2 pi over the period, which is equal to 2 pi over 12, which is equal to pi over 6. So for this equation, I have y equals my amplitude, which we said was 27.5, and it's negative 27.5 because it's not starting up, it's starting down at your minimum and going up. So then we have times the cosine of my b value, which we just said was pi over 6, times x, and I don't have a phase shift for cosine, plus my vertical shift, which is 32.5. Oops. So this would be one equation. Another equation, if I did sine, would be y equals, and if we start here on my graph, that would be a positive value because you're going up and then down. So 20 or 30, so 27.5, because that's my amplitude, times the sine of pi over 6 x minus 3, because I had to shift my graph to the right 3 to get here, and then plus 32.5. So that would be my sine graph. Of course, there are many other equations that I could have picked. Then it says we want to predict the height above the ground when t equals 9. So in this case, they're saying instead of x, they're using t. So really we're saying when x equals 9, how high above the ground am I? Well, I would then plug this into my equation, y equals 27.5, and it doesn't matter which equation you do, I'm going to do cosine times the cosine of pi over 6 times 9 plus 32.5, and without even having to do any of this, I know that by looking at my graph, I'm going to be at this height right here, which is 32.5 feet. If it was not one of my key points on my graph, then of course I would go ahead and make sure to plug it into my calculator, and I would use radian mode and then figure out what the value would be equal to. So let's do another application problem. So example 4 in the back, it says, suppose that you have a weight hanging from a spring set in motion by an upward push. So that's important. It takes 5 seconds for it to complete one cycle of moving from its equilibrium position to 8 centimeters above, then dropping to 8 centimeters below, and finally returning to its equilibrium position. Now, we're also taking note that this is an idealized situation where the spring, we're going to say, has perfect elasticity and friction and air resistance, etc. All that stuff is negligible. So we're not taking any of that kind of stuff into consideration. We're going to first sketch a picture of the weight. So my weight equilibrium position would be on the x-axis. So this is actually the equilibrium position. Now for this, it says that we're going 8 centimeters above and then dropping below. So I know this would be 8, and this has to be -8. It also says that it takes 5 seconds to complete one cycle. So that means that the period is equal to 5. So if the period of my graph is equal to 5, then I know I can find the key points on my graph, which is what I need. So my key points then are going to be 5 divided by 4 equal parts, which of course we know is 1.25. And so that's what I'm going to count by for each of the points on my graph to get each of these values. So here we have 1.25. Add 1.25 plus another 1.25 and you get 2.5. Plus another 1.25 is 3.75. Plus another one would give me 5, so that makes sense because now I'm at the one wavelength. And remember, it said that it's set in motion by upward push, and it tells us that to complete one cycle, moving from its equilibrium position to 8 centimeters above and then dropping below. So that means we're starting here at 0. Then we're going to 8 centimeters above, coming back to our equilibrium position, coming below, and then back here for my last part of my wavelength. So this is what the sketch of the graph will look like. Now, again, I know my amplitude is equal to 8, because that's where we're moving from our equilibrium position. In this case, I had no vertical shift. And if I'm doing a sine graph, then I have no phase shift. If I'm doing a cosine graph, then I would have a phase shift of 1.25, or I could do 3.75 if I did a -1. Then it says find a sinusoidal function to represent the motion of the moving weight. If it doesn't specify what to use, then I would use the easiest one, which has no phase shift. In this case, it's sine. So we have y equals my amplitude, which is 8, times the sine, because it's starting on the x-axis and then going up, of my b value. Well, we haven't found our b value yet. We have the period, which is 5. So to find my b value, remember it's 2 pi divided by the period. So in this case, 2 pi divided by 5 would be my b value, times x minus, in this case, we don't have a phase shift, so actually I don't need to write that. So just 2 pi over 5x, and then I have no vertical shift. So this would be the equation for a sine graph. If it said to come up with an equation for a cosine graph, which it didn't, I would do y equals, and I would use this point right here. So that would be y equals 8 times the cosine of my b value, 2 pi over 5, times x minus 1.25. That would be the equation for a cosine graph. C says we want to use your function to predict the height of the weight after 3 seconds. So then, of course, we're saying, well, when x equals 3, what does my y value equal to? So, of course, I would plug this into my calculator. So if I plug this into my calculator, I'm going to go ahead and do 8 times the sine of parentheses 2 pi divided by 5 times 3. Make sure I close the parentheses there. I'm going to make sure I'm in radian mode, which I am, so I can quit out of there and hit enter. And it looks like about -4.7 centimeters below the equilibrium. So I would write that our y value is equal to negative 4.7 centimeters below the equilibrium position. And of course, if you look at your graph, you can see if that kind of makes sense. Well, if I have 3 seconds, that's going to be somewhere in here. So somewhere in here would be negative, and so it looks like about halfway in between, so negative 4.7. So we did good there. Then the next part says, in the first 5 seconds, when will the height of the weight be 6 centimeters below the equilibrium position? So this one's a little bit different. Now we're saying that we want to figure out when it's going to be 6 centimeters below the equilibrium position. So we don't do anything with the 5 seconds, but this is our y value. So 6 centimeters below would be negative 6 equals 8 times the sine of 2 pi over 5x. And in order to solve this equation, I'm going to plug this into my calculator, and I'm going to do the intersection. So I'm going to plug this into y1, and I'm going to plug the other part into y2. So we have negative 6, and then I have my equation, which is 8 times the sine of 2 pi divided by 5 times x, close parentheses. And I need to change my window. So I'm going to change my window from 0, and then I would use the first wavelength, which is 5, or you could do twice the wavelength, it doesn't really matter. My key points are going by 1.25, so I like to always put those in. And I know that I'm going to from negative 8 to 8. So I'm going to change that window for my y max and min as well. And then I'm going to hit graph. So there's my y equals negative 6. Here's my graph. So I see it hits here and here. Let's go back to the question. It says, in the first 5 seconds, when will the height of the weight be 6 centimeters below the equilibrium position? So for this, we have 2 answers, because it didn't say when it's going to hit first. It just says in the first 5 seconds. So if you look here, you have this solution and this solution. So to find it, second trace, we can do our intersection, number 5. And then remember, you go close to the intersection and hit enter 3 times. 1, 2, 3. So we get at 3.17 seconds. And then if I do the intersection for the other point, and hit enter 3 times. Oops. Try that again. We get 4.33 seconds if we round. So x is equal to 3.17 seconds. And then we get x is equal to 4.33 seconds. Okay. So we have one last question here. And I'm going to have you guys finish this, but I'm going to start it with you. It says that, let me erase that right there. A wheel with a radius of 2 centimeters is rotating counterclockwise at 3 radians per second. A free hanging rod 10 centimeters long is connected to the edge of the wheel at point P and remains vertical as the wheel rotates. For A, it says, assuming that the center of the wheel is at the origin and that the point P is at 2, 0 at time t equals 0, find a function that describes the y-coordinate of the tip E of the rod at time t. And then B says, what is the first time that the tip E of the rod will be at a height of -9 centimeters? Now, the trick for this one is figuring out what one wavelength for your equation is going to be. So if your wheel is rotating at 3 radians per second, well, how do we figure out what the time it is going to be to complete one revolution? So remember that distance equals rate times time. So the distance it takes to go all the way around would be 2 pi is equal to my rate, and of course my rate in this case is 3 radians per second times time. So we're just solving this equation to figure out what the time is that it takes to complete one cycle around my circle. So t would be equal to 2 pi over 3, and this is the period of the function. So now I want you guys to complete A and B and see if you can answer the question. So you complete A and B for class. And just bring that with you.